Hello everyone, let's learn about the logarithmic scale. In Python, when you want to compute logarithm of a number y for a given base, you can use the math module log function. This function takes two arguments. The first argument is the number y for which you want to determine the log, and the second argument is the base that you want to apply. We are going to specifically focus on log base 10. You can use the log10 module inside the math function, which takes one argument as the number for which you want to determine the log base 10 value. The expectation here is that, excuse me, you want to find a number x such that 10 to the power x equal to y. For instance, log base 10 of 1000 is going to return a value of 3. That's because 10 to the power 3 is 1000, correct? What we are going to do today is, we are going to come up with an approximate definition for log base 10, which is not completely accurate, but it is very easy for you to understand. I'm going to define this function as log underscore approx. The parameter name is going to be y. The argument that you pass for this parameter y is going to be subject to two specific conditions. Condition number one is that your argument should be of integer type always. So I'm simply going to assert type of y equal to int. Condition number two is that you should pass at least a value of 1 as an argument. So I'm simply going to say y should be greater than or equal to 1 here. The approximate definition itself is really simple. You just need to be able to count the number of digits in the number y here. There is a very straightforward way to do that in Python. You can convert y into a string, and you can use the len function to count the number of characters in that string sequence. So I'm simply going to convert y to a string, and I'm going to call the len function, and that should give me the number of digits in the variable y over here. I'm going to go ahead and return that computation. Let's call the log underscore approx function for a large number, say 1, 2, 3, 4, 5, 6, 7, 8, 9. Are you able to guess what is the result of this function call? If you guess 9, then you had the correct answer. There are 9 digits here, right? Let's take a look at the actual log base 10 value for this number. That's 8.09. That's not a bad approximation, correct? Let's try one more value. So I'm going to try 989898. That should give 6 here. Let's take a look at the actual log base 10 value. That's 5.99, which is really close to 6 over here. A natural follow-up question here would be, what would be the error margin for a range of numbers? Let's try a million numbers here. So I'm going to say for I in range of million, and what I want to be able to do here is, I want to be able to compute the error margin for all the numbers from 1 through 1 million. I need to be careful here because the range built-in function call iterates from 0 through end minus 1. So I'll have to say y equal to I plus 1 to ensure that my for loop finds the error margin for numbers 1 through million over here. So I'm going to call log underscore approx function on y, and I want to be able to compare that with the actual log base 10 computation on y. I don't really care if log underscore approx returns the higher value or the lower value. So I'm going to take absolute of this difference by calling ABS function. This is the current error. I want to be able to track all of these errors. So I'm going to define an errors list outside my for loop here. And I'm going to append the current error into errors list by using the append method call. After computing all the errors for the numbers 1 through 1 million, I just want to be able to find the maximum error margin here. So I'm going to say max of errors. It's going to take a while for us to run this cell. Looks like the maximum error that we are going to encounter is 1, which is not bad. So you might be wondering, why exactly does all of this matter? Whenever you want to plot some series or some column of a data frame which contains really small values and also really large values, you want your plot to meaningfully represent both the small values and the really large values, correct? When you're comparing a really small number with a really large number, you don't really care what digits are there in the small number and what digits are there in the large number over here. What you rather care about is the number of digits in the large number and the number of digits in the small number, correct? That's exactly what log to the base 10 scale enables us to represent. It enables us to represent numbers in the powers of 10. Log base 2, on the other hand, enables us to count how many bits we need to represent a particular number. I'm going to demonstrate the need for log scale by showing you a line plot from a series of numbers. Let me first define the series of numbers. So I'm going to create the series from a list of numbers. So I'm going to say 1, 10, 100, 1000, and I just want to keep adding zeros as I keep going up over here. Let me capture the series into a variable s over here, and I'm going to create a line plot from the series. I can do that by saying s.plot.line, and recall that that will create a plot which has a single line that represents all of these values in the series over here. Notice that the plot is really unreadable for the initial set of numbers. You can barely differentiate between 1 and 10 and 10 and 100 because of the presence of million over here, right? What you need here is a logarithmic scale for the y-axis. There is a very easy way for you to define that. You can just pass an argument of 2 to the parameter log y. Since we want the y-axis to be log scale, the parameter name is log y. You can very easily remember that. And I just need to pass the argument as true. That's so much better now, right? At least I'm able to compare 1 with 10 power 6 over here. How many zeros you have in your number determines how far up on the step line you are, correct? So logarithmic scale is really important. Let me quickly show you an example with the stock market dataset, which is the SP500 dataset that we covered earlier as part of the topic of plotting. Recall that we plotted the earning that we would get if we were to invest $1,000 in 1970 in the SP500 index. If you were to just look at the earnings plot as such, it makes you feel like it's not really useful to invest in the period between 1970 and 1990, right? Because the plot here is deceivingly showing an exponential rate of increase from the 2000 to 2020. What you need here is you need to be able to look at the y-axis using a logarithmic scale. You can look at the plot below here, which shows the exact same information in a logarithmic scale. As you can see, this particular plot always has an exponential growth. So it's often misleading when you have a plot which has really small numbers and also really large numbers put together within the same plot. So you have to always be careful to use logarithmic scale whenever it is applicable to compare really small numbers with really large numbers. I'll let you go through the rest of the reading text about this particular example to get a better sense of what I'm explaining here. The final thing which we are going to learn in the topic of plotting is how to generate multiple plots within the same figure. And we are going to use pyplot for that. Recall that we have already used the subplots function inside pyplot. Pyplot can be imported from matplotlib, and a lot of Python programmers abbreviate it as PLT, so we are also following the same convention. So I can create a subplot simply by saying plt dot subplots, and that's going to return a tuple of two values for me. The first one is the plot figure, and the second one is the axis subplot object. We've been using the axis subplot object a lot throughout the course of plotting topic lectures over here. So if you want to create multiple plots within the same figure, you can just pass argument to the parameter which are n columns and n rows. N columns would enable you to have two plots as two column figure over here. N rows would enable you to have two rows within the same plot, so that will split the figure into a top plot and a bottom plot over here. N column splits the figure into a left plot and a right plot. Of course, you can use both of those together, so you can say n rows equal to 2 and n cols equal to 2. That's going to create a 4 plot figure, 4 plot diagram within the same figure. Let me show you why this is useful. So I'm going to give you a couple of examples over here. What we are going to do is we are going to first of all capture the return value of the axis subplot object that gets generated whenever you call the subplots function. So I'm going to go ahead and create two vertically split plots over here. Let's take a look at this return value really quickly. So you get tuple as the return value from subplots function. The first entry is for the figure, and the second entry here is what is called as numpy array. So it gives you an array of, actually it's a regular array, excuse me for that. It's a regular array. Array works very similar to a list, at least for the purpose of this course. You only need to know that indexing is a supported operation in an array. And if you go through lab P13, you'll learn slightly about numpy array, which is also going to give you the exact same description. You are not expected to know anything more about arrays. So this particular array, which you can think of as an equivalent of a list, has two axis subplot objects. So that's going to represent both of these plots within the same figure over here. So let's take a look at which one of those will enable us to plot on the left side and which one of those enable us to plot on the right side. I'm going to capture the return value and also apply tuple unpacking. So I'm going to say figure for the first tuple entry and AX for the second tuple entry over here. So if I go ahead and print AX, you'll see that we are getting two items as part of this array. So I can simply access the first item of this array by saying AX of 0, and I can access the second one by saying AX of 1. Let me actually define this variable as axis because we have plural of axis subplot over here. So I'm going to show you how you can plot on the left plot and how you can plot on the right plot. Let me first go ahead and create a series. I'm going to create a series by creating a list of numbers. So I'm going to say 1, 2, 3, 3, 4 over here. And if I say dot plot dot line, and when I just say ax equal to axis of 0, what's going to happen is, sorry, looks like I missed an E here, let me fix that. What's going to happen is that's going to create the plot on the left side over here. If I want to plot on the right side, I'll have to say axis of 1. So what I'm going to do now is I'm going to show you two plot example series within each of these subplots on the left hand side and on the right hand side. I'm going to create another series. Let me go ahead and plot the first series in the left hand side, and I'm going to plot the second series on the right hand side. Let's use different values for the second series. Let's say that I'm saying 5, 7, 7, 8 for the second one. So if you just plot those as such, notice that your plots are extremely misleading. So you need to always follow a rule of thumb when it comes to plotting multiple plots within the same figure. If you're using a vertical split, your y-axis should be always shared. If you're using a horizontal split, your x-axis should always be shared. So the correct way to plot this particular figure would be to say you want to share the y-axis here. So you can do that by passing an argument of true to share y argument here, which is going to be an argument for subplots function. So that will just make the plot so much better to read. Now we are able to easily say that the plot on the right side has higher numbers when compared to the plot on the left side over here. Right, that will be it with respect to the plotting topic discussion. I briefly want to show you the plot design examples that are mentioned as part of today's lecture reading. So what you have in that particular section of the reading is that you have a series of examples where you take the same data and plot it using two different types of plots on the left side and on the right hand side. For example, example number 1 gives you spending for different agencies. The question here is, do you think the plot on the left side, which is the pie chart, is better, or the plot on the right side, which is the bar chart, is better? I would say 90% of the time the bar chart would always be better. One of the main reasons for that is you can take a look at absolute numbers in the bar chart, whereas in pie chart it's very difficult to do that unless you actually display the absolute number as part of each pie over here. Another specific thing with respect to this particular example is that it's very difficult to look at this pie chart and say whether police has higher spending or school agency has higher spending. Whereas if you look at the bar chart, it's quite evident that schools has higher spending over here. Also, it depends entirely on context. If you just want to talk about percentage of spending, then a pie chart would be really good. If absolute numbers matter, then definitely a bar chart would be the better type of plot over here. So what you'll notice is if you scroll all the way to the end of this reading, the list of plots which Tyler and I and Mike think are more appropriate is provided over here. Let's go through a couple of other examples. So let's go through this example over here. Notice that we have a data frame which we create from a dictionary of lists here. We have a set of values for A and then a set of values for B over here, right? What do you think? Do you think plot on the left hand side is better or plot on the right hand side is better? I personally think the plot on the right hand side is better. One of the things with stacked bar plots is that the bar plot which is going to be closer to the x-axis always has an edge, right? Because you can say the trend for that particular bar plot. With both of these options, it's very evident that there is an upward, lowered trend with the variable a here, right? You can get that from the right side option also, but the trend for variable b is not really evident from the first stacked bar plot version, whereas on the right side it's very evident that you have a small increase in the variable b. So I think the right side version is a better example when it comes to this particular comparison between these two plots. I'll go through one other example. In this example, I want you to focus on the fact that we have a list of a dictionary of lists. We use that to create a data frame. Notice that both a and b variables have the exact same values. So what's going to happen here is on the left, you have a regular stacked bar plot. On the right, you have a logarithmic scale on the y-axis. Notice that whenever you have a logarithmic scale, whatever bar plot is closer to the x-axis is going to have an edge, and that's going to always look bigger. Basically, the plot on the right completely misrepresents the data. If you just take a look at the logarithmic scale plot over here, it's very easy for you to think that A has a higher value than B, but that's simply not true because A and B have the exact same values. I would recommend you to not use logarithmic scale on the y-axis when it comes to stacked bar plots because it doesn't really make any sense for you to do that. Even though the plot on the left hand side is barely readable for the first two values, at least it's not misrepresenting the truth. Right side is simply misleading, so you should prefer the plot on the left side over here. All right, that will be it for plotting lecture. I'll wrap up the lecture here.